Hello, everyone. Thanks for coming to this talk. Today, I'm going to talk about the memory model inside Spark. So as you know, Spark is coming out as an in-memory computing engine. So knowing the memory model inside Spark is kind of important and maybe helpful for you to use Spark more efficient and for troubleshooting in Spark applications. So a little more about myself. I'm a software engineer at Databricks, and I'm a Apache Spark committer. And also, I'm pretty active in the Spark community. So if you are also a Spark contributor, you may know my GitHub ID, CloudFan. And a little more about my company, Databricks. Our company is founded by the team who started Spark project in App Lab. And our mission is to provide a platform to make data simple. Okay, let's go to today's topic. So first of all, Spark is an engine that is close clusters. So it's very important to understand the resource management across clusters. A typical Spark cluster consists of a single master and several workers. So if we use like other resource manager like Yarn methods, it will be something similar, but with different names. And if a user writes some Spark programs and submit to the applications, submit its application to Spark, so it will require a Java program in the cluster in any nodes. And then the master will assign several executors for this Java. And then this one Java and several executors is the machine or is a unit to run your Spark jobs. And then simultaneously, other users can also submit his Spark applications and launch another Java and executors. So the resource manager, I mean the master and the workers, is responsible to allocate the resource, including CPU, memory for these applications. And inside each executor is actually a JVM process, and which has a small memory manager to manage the memory for this process, and then a third port to run your task, because Spark will split your jobs into smaller tasks, and each task will belong in the slot in the third port. So today, I'm going to talk about the memory manager inside one executor, not the cluster level. Okay, let's start to see how the memory model is inside one executors. So for a typical query, first of all, you have to read data from a data source. So for example, you want data from packet files, maybe JSON files or other stuff. And then the data will be loaded to Spark with an internal binary format. And after that, we will have many operators to run your data, to process data and produce results. And then we have a memory manager so for you to allocate and free your memories. And also, if one beauty of Spark is to allow you to cache your data, so that if you want to process it more times, it can be very fast. So today I will walk through this diagram one by one. First, I'm going to talk about the memory manager in Spark. And similar to many systems, Spark will allocate the memories in page granularity. So that means each operator should allocate the memory, maybe one page or several pages. And this is a very common practice in many systems. And also, Spark supports off-heap, which means your allocated page can either be JVM heap or off-heap. And also, there's one special property for Spark memory manager. So the page in Spark is not fixed size, but it has a lower and upper bound. And there's another special property of the memory manager in Spark is that there is no polling, which means if you allocate a page and you use it up and you want to free it, it will be freed right away. So you cannot reuse a single page again and again. And somebody may ask why Spark does this. So why Spark choose to use a var-length page and there's no polling for the page? Okay, it's kind of a trade-off inside Spark. So the pros of using the var-length page and no polling is, first, it can simplify our design. So because the page is var-length, so I can put my record in a single page, always in a single page. So there will be no single record across page boundaries, and it will be easy for us to design the format to put on the page. And also, because there's no polling, so once a page is used and freed, the OS can get this freed memory immediately, and then it can use the memory for other stuff like the file buffer or other caching. So it's a trade-off. So we also have counts. So what are these counts for var-length page and no polling? So first, because like I said, a single page, a single record have to be put in a single page. So if there is a record which is very, very big, and then Spark will fail to load it. And actually, this is very rare in the actual world because the upper bound of the page in Spark is 16 gigabytes. So it's very rare to have a record, a single record to close as 16 gigabytes in memory. So as for now, we don't have any problem for this limitation. And the other thing, which is very common for var-length pages, is fragmentations. So because you have the very different set of pages, and your memory will be divided into these different chunks, and then your memory allocator will have problem when it frees and clear these pages. And this problem is actually not very heavy, not very seriously in Spark, because we have remember we have a lower bound for the page size, and this lower bound is also very big. It's about several megabytes. So in the most case, one record will not hit this lower bound and can acquire a fixed size page at this several megabytes. So it means inside Spark, when Spark processes data, mostly it will allocate fixed size pages as like other systems. And the last one is actually a real problem. So because we Spark frees the page right away, it means we have an overhead for the memory allocation. Because if you have polling to reuse the pages, it means for the OS, you only allocate the memory once and then never allocate again. And for Spark, it will actually free the memory. So we will have a little overhead in the memory allocation. And because of the nature that in most cases Spark will allocate fixed size page, it's actually not a very big problem because most of malloc algorithms can work well with this case. Okay, next I'm going to talk about the internal format inside Spark, which means what the data looks like when you load it into Spark memory. A very simple idea is to use Java objects because Spark is written in Scala and running in JVM. So it's very natural to use Java objects to represent data in Spark. So here is an example. So for example, I have a record which has 3 columns. And the first column is int, let's say 123. And the second and third column is string type, which is data and bricks. Okay, so this is a memory layout of this object in JVM. So first, we will have a row object containing this is the public interface for this record. And then in this row object, we will have an array to contain the actual data. Here is the 1, 2, 3 data and bricks. And then inside this array, it has 3 elements. And because in Java, the array have to have a type associated with it, so it has to be object. So here, for the 1, 2, 3 int, we will have a box integer class for this value. And for string, we will have the string class. And this is actually a very expensive memory layout for data. So as you can see, there are many objects in this layout. And also, for a very simple int type 1, 2, 3, it's actually use a box integer class, which is way more than 4 bytes in memory. So which means this has very high space overhead. And also, because of the boxing, the value accessing is also slow because you have to do unboxing before do something else with the value. And also, a very common function that we require for data is to call hash code because we want to compare, we want to do equal check between records. And for this memory layout, the hash code is also very expensive. You have to go through so many objects to calculate hash code and compile them together. And there are also some other disadvantages to use the Java objects to represent data. So first, it's very hard to monitor and control the memory usage because different JVMs may have different layout for objects. So you may have slightly different size for a same object. And also, many of you may know that GC is really a problem for JVM. So if we use a lot of JVM objects, the GC will be a killer for our program. And also, for Spark, it needs to transfer the data between nodes. So we have to serialize the data, the JVM objects, to bytes and transfer it to another nodes and deserialize it again. So if we use Java objects, the serializing cost is also a big problem. So inside Spark, we use a very efficient binary format to represent a record. So in general, this format is consisted of 3 parts. First part, the non-checking part, the non-bit part, and the second part is the address part to store the address where the data stores, and the third part is the data part. So let's see example. So for this example, the record 1, 2, 3 Databricks, and first we will store the information in the non-bit part. So this is used to quickly tell if a column is null or not. And then we began to actually put the data in this format. For the first column, 1, 2, 3, is the int and its fixed size. So we can just put it in the address part. For the second column, it's a string and it's a var-length data type. So we have to put the offset and the length of this data in the address part, and then we put the actual data in the data section. Same to the third column. So after this, we can have a very efficient format for the records in Spark. Okay, now we have internal format for records. How can we process these records in Spark? Here is a simple example. So for example, here I want to read a JSON file, and which only has 2 columns, I and j, and I is an int column, and j is a string column. And then I want to do a simple filter to get the records that is I greater than 0. And then I want to do a substring for the column j. So what is the data flow? So first of all, is the data source, the JSON files, and then we load the data from JSON files into memory row by row. And let's say the first row is like 2 columns, 1, 2, 3, and the data. Okay, then we come to the filter operator. So how we can implement a filter and let it to evaluate on this format. So here we know that the column I is the first column and it's an int type. So we can know that where the int value stores. So here we just address this value into this binary format and read it out, which is 1, 2, 3, and we just compare it with 0, and for this case it's greater than 0, so we pass this filter. Okay, next is the project operator. So how can we operate on this string type column? So again, we will read the address from the using the offset and length from this address section, and then we point to the actual data section, and then we read the data, and then we do a substring to get the second to get the first 2 characters of this string, and then we write this data to a new record, which is also binary format. So after this, now we have a complete workflow, a data flow to read JSON files, do some computation, and output it with all in binary format. So now you can see that Spark has a very efficient way to process data. But then there's a problem that comes out. How can we do it better? To answer this question, I have to introduce some background knowledge. It's about CPU cache. So long time ago, when the computer is first invented, there is no CPU cache because at that time, CPU and memory are all very slow. So there's no gap between CPU and memory. We can just read the data from memory in CPU instructions. However, as the time goes, we have the CPU becomes faster and faster, and there is a very big gap between DRAM and the CPU. So now, if we always read the data from memory when we evaluate CPU instructions, it will be very slow because CPU has to wait the memory to return. So how to solve this problem is using the CPU cache. So we can prefetch some data into CPU cache, and then when we run some CPU instructions, we just read the data from cache, and which is very, very fast. We don't need to wait. Okay, and then knowing this knowledge, how can we leverage this to improve the Spark performance? So one idea is we just rewrite the entire Spark, entire operators of Spark to use this CPU cache knowledge and make it better. But that is a lot of work because there are so many operators in Spark like filter, join, upgrade, project, blah, blah. So a very smart move is to only focus on two important technologies in Spark, which is sort and hash. This is because in the big data world, sort and hash is the most fundamental algorithms, and many other fancy algorithms is built upon this. So let's see how Spark improves the sort and hash with the CPU cache knowledge. First, let's see an example of a naive sort. So that is how you will do to implement a sort. So you will have a memory region to keep all the pointers of your records, and then you have another memory region to keep the actual data. So here we have 3 records, BBB, AA, CC. So when you want to sort these records, first you will pick up 2 records, and then do a comparison. And here we found that AA is smaller than BB, so we switch the pointer. So here we switch the pointer instead of switch the data because the data move is very expensive. Okay, then we repeat this step again and again to sort all the records. And what's the problem? So the problem here is each comparison needs to access 2 different memory regions because we first need to read the pointer, and then we need to dereference the pointer to the actual data and read it. And this means the CPU has to read the data between 2 memory regions again and again, which makes it hard to guess which data will be fetched next for the CPU, and which will result to very poor cache locality, and also which will result to very poor performance. So how to improve it? So here, the underlying idea of this algorithm is that, so assuming you are comparing 2 strings, so what you will do is to compare the characters one by one. And mostly you will find out that maybe you can just compare the first 8 characters of the string, and you can get a result. So the idea is that we can store a key prefix of your record with the pointer. So the key prefix and the pointer are in the same memory region. Now let's say how you can sort these records. Again, you pick 2 records, the pointers, and then you just read the key prefix and compare the key prefix. If it's done, then just switch the pointers, and you don't need to go through the actual data to the full compilation. So this can dramatically reduce the time you jump between 2 memory regions, which results to a very good cache locality. Because now your data access mode is more like a linear fashion. Okay, the other important technology is hash. So because hash map is heavily used in Spark, how to improve is very important to Spark. So here is a very naive implementation of hash map. So again, we will have a memory region to store all the pointers of your records, and then we have another memory region to store the key and value of your records. So when we look up a key, what we do is first we hash this key, and we model the size of the hash table and to get a position to look up in this hash table. And then we get a pointer, and we dereference this pointer to get the actual key and compare these 2 keys. So as you know, in a hash map, especially in a hash table, the hash collection is very common. So in this case, the key 2 and key 3 are different, and then we have to look up again, use quantitative probing to find another entry to compare. And this time, okay, we found the key match and return the value. So what's the problem of this approach? Let's say if we are very lucky that we have no hash collection, then this way is doing very good because we only need one lookup and just delivers the pointer and get the value. However, if the hash collection is a lot, which means for each lookup, we will go through this pointer memory region and the key value memory region many times. And this will result to very poor hash locality and bad performance because we are jumping. The CPU is jumping between two memory regions. So in Spark, we also introduced a cache-aware hash map to fix this problem. The idea behind this is that although the hash collection is very common for a hash table, but if you compare the four hash value of your key, then the collection will reduce a lot. So the idea is we can store the four hash value of your keys along with your pointers. Then when we do a lookup, we first, like previous, we hash the key, and then we mod it by the size of hash table and get the position of the hash table and do a lookup. And then instead of delivering this pointer to the actual keys, we just compare the full hash value between the lookup key and the key with this record. If it doesn't match, we just use the quadratic probing and find the next entry to compare. And now if the full hash value matches, we do the difference and get the actual value. So this means in an environment that has many hash collections, this cache-aware hash map can dramatically reduce the time you jump between two memory regions and give you a very good cache locality and good performance. So here is a quick recap of the cache-aware data structure in Spark. So the way Spark picked to improve the cache locality is first we store the key prefix with pointer to improve the sort, and then we store the key's full hash value with the pointer for the hash map. So in general, we store some extra information to try to keep the memory accessing in a single memory region to get a good cache locality and improve the performance. Okay, let's go back to this diagram. So now we actually covered most parts of this diagram, except the cache manager. And I won't cover this because it's very simple, because just keep this binary data in the heap and free it when you want. And one thing I want to talk about is the data source. So if you look at this data flow, once data is loaded into Spark, it can be very efficient because Spark keeps the data in binary and processes it with binary. However, the bottleneck of this data flow is at the beginning. When we load the data from data source, how can we improve this? So this is in the future work. So someone may notice that, hey, Spark has a binary format. Can we just produce my data with this format to Spark? The answer is no, because this format is designed for internal use only, which means we may change it across Spark versions, and it's unstable to use in public. So one work we want to do is to publish a stable format for Spark records, and it will not be a low-based format. So the format I introduced before is a low format for a single record, and what we want to do is to introduce a current format, public current format for the data source, because nowadays the current format is becoming more and more popular in the big data world. So if we can provide a public current format for the data source, they can provide a very fast implementation to feed the data to Spark. And also there's another ongoing work is data API v2. So for the current data API, it's kind of weak because first it only has field pushdown and column pruning, and no other fancy stuff like sort pushdown, partition report, and limit pushdown, and column reader, and other so on stuff. So we want to provide a flexible API for new data source, which allows you to do many operations like join push down, agree push down, kernel reader, and blah blah. And it can also guarantee very strong backward compatibility if we add new functions in the future. And also, another point is we want to have a current execution engine. So because the data, when we load data into Spark, it will be in kernel format if we accomplish the first two tasks. And then it will be great if Spark can process data in kernel fashion. For now, as you know, Spark SQL is kind of a compiler that compiles a query into Java code. And in the Java code, we just use maybe a for loop or maybe a while loop to process the data one by one. So if we can change that to process a bunch of records at a time, it can boost the performance even better. Okay, that's basically it. It will be great if you can try Spark in Databricks. It's free. And thank you.
Awesome. Thank you so much, Wenchen. Unfortunately, we don't have time for questions right now, but you can talk to Wenchen right now. So thank you so much. We'll have lunch for the next hour, and the talks will resume at 2 o'clock this afternoon. Thank you.